Hello all, I'm Tamil Shelvi, Associate Professor, Department of ECE, Jerusalem College of Engineering, Chennai. In this presentation, we are just going to see about Unit 1 of EC 8552 Computer Architecture and Organization, one of the core papers for the ECE students of affiliated institutions under Anna University. So Unit 1 deals with computer architecture, computer organization and instructions. Let us see about it in detail. So let's start with the 8 ideas with which the computer designers work or start working on the architecture of the computer. One of the constant issues for the computer designers is the change that occurs, and this is driven largely by the Moore's law. Now, the Moore's law states that an integrated circuit resource is doubled every 18 to 24 months, and this prediction is taken right from 1965. Now, this is designed by Morse, and this law is taken as the basic structure for designing any computer, a new computer to be developed with. Now the graph is drawn with the year against the IC used or developed in that year. The second law with which the designers start designing is the abstraction to simplify the design. Both computer architects and the programmers have to invent or should have an inventive idea so that they can be more productive. Now this productivity will come with the use of abstractions so that they can represent the design at different levels. Now when they start representing their design from the lower level and slowly develop it to a higher level, a model is easily developed. So use of abstraction to simplify the design is the next idea with which a computer architects start design. The next point on which the concentration of the designers lie is to make the common case fast. Now, making the common case fast will enhance the performance better than optimizing a rare case. What does this mean is, instead of taking a very rare case, identifying the rare case, keep working on how to get it optimized, how to make it work better. Instead, take an easier issue, work on it so that the work is done faster than the rare case. Now, this is going to be common, as well as the main advantage of this is the work is going to be simpler and also easier. Next is performance via parallelism. The architects have offered design by performing the operations in parallel. Instead of doing it one by one, multitasking is being done here by doing parallel operations. An instruction is being divided into multiple subnodes, submodules, and then get it assembled after doing it. So that is going to be improving your performance. So performance via parallelism. The performance also can be improved or enhanced by the way of pipelining concept. So pipelining is an implementation technique in which multiple instructions are overlapped. So this will improve your performance by increasing the throughput of the instruction also. Example, if there is a fire, you can always see person carrying bucket of water. They will not run from end to end. Instead, they will stand in a line, and only the bucket of water is being carried or is being moved from one person to other. That is the best example of the pipelining concept. So let's move on to the next point. The next one is improving the performance via prediction. Uh, Now, to get a better, we know the saying that it is better to ask for forgiveness than for asking permission. So next way is going to be your next way to increase your performance is via prediction. So in some cases it can be faster, because you guess it how it is going to work, and it is sometimes it is going to be faster, but sometimes it may be not very sure. The output may not be very sure. But with the experience, with the past history and the past experience, the designers should be able to improve the performance via the prediction. The most the important advantage of this is it is not going to be very expensive, and the prediction has been relatively accurate in many design till date. So you can improve the performance via prediction also. Hierarchy of memories is the next point that has to be concentrated on. The programmers want the memory to be very fast. Yeah, they want it to be larger. They also don't want to compromise on the cost. So the speed often shapes the performance. The capacity limits the size of the problems, and the cost is often the majority of the computer cost. That is known to all of us. Now, if this is being achieved at an optimal way, then it is going to be easier. So the architects have found that they can address on these conflicting demands with the hierarchy of the memories: the fastest, the smallest, and the most expensive, then versus the slowest, largest, and the cheapest for the bottom, and to categorize it between the top and the bottom, then it is going to be easier for the architects in designing a system. Now, cache memory is another thing that we have to concentrate on here, which we'll see a bit later. Now, the last point on which the designers view is on the dependability via redundancy. Computers should not only be fast, but they need to be dependable. So since any physical device can fail, systems can be made dependable by including redundant components. These components are going to take over once failure occurs, so that the work of the system is not stopped. So while designing the system, we have to keep in mind, the architects have to keep in mind all these issues, so that keeping this as the base, they will be able to easily design the system. The next topic that we are going to see in Unit 1 is the computer as components. The 5 classic components of the computers is what we are going to see here. The first one is the input, which we know it writes the data into the memory. The second main component is the output, which reads the data from the memory. The memory is the one which is going to store the data. There are two types of memories that are going to be available inside a system. One is going to store the data, and the other one is going to store the instruction or the program. Now, the most important part of the computer is the control unit, which is going to generate the control signal and send it across the system units that is present in the system to determine which operation is to be performed. From where the data has to be taken till where it has to be saved is generated from the control unit, and the signals are sent across. Then finally, you've got the data path, which performs the arithmetic and the logic operations. These are all known issues, known components for us. Now let's elaborate on the components of the computer system. The input device is the mechanism through which the computer is going to be fed with the information through the device, the input device. So the most commonly used input device is a keyboard, and it works based on the principle: whenever a key is pressed, the control signal is generated and sent to the processor, thereby the corresponding data or the character is displayed. The next most commonly used input device is the mouse. Whenever you roll on the surface, whenever you roll a mouse on the surface, then it would cause a XY counter to be incremented, and thereby identifying what has to be what data has to be clicked on, or what data has to be displayed. Now, the output device, when we talk about the output device, It is a mechanism that is going to convey the result, whatever has been computed by the system. And one of the most fascinating device is the IO device, maybe the graphics display. Today, most of the LCDs uses active matrix that has a tiny transistor switch that will help in making the display bit sharper, so that you can get a very clear image. The computer hardware supports a refresh buffer or a frame buffer to store the bit. This output data, the computer data, is stored as bits. So the computer hardware is going to is supported with a buffer or a frame buffer, which is to store the bitmap. The image to be represented on the screen is stored in the frame buffer, and the bit pattern per excel is read out to the graphics display at the refresh rate. It depends on the refresh rate. Now, pixel is the smallest element how we represent a picture. The screen are composed of thousands and millions of pixels, and it has to be organized in the form of a matrix. So each coordinate in the frame buffer on the left determines the shade of the corresponding coordinate for the raster screen CRT display on the right. Here, the pixel x0, y0 contains the bit pattern 0011, which is the lighter shade of gray on the screen than the bit pattern 1101 in the pixel x1, y1. It's just an example, and this is how it is being displayed by using the output device. Now, the next component we are going to elaborate on is the processor. So the CPU, which is called as a central processing unit, is the active part, which contains both the data path and the control, which can do testing of numbers, adding of numbers, signaling of IO is done by this processor, and the data gets instructions and the data from the memory. The data path is one which the component of the processor that performs the arithmetic operations, and control unit is the one which will give the commands. Maybe a data path or a memory or a IO device. All these components get instructions, commands from the control unit. So these two will form the processor. The data path and the control path will be the part of the processor. The next component that we are going the next component of discussion is the memory. This memory is nothing but a storage area in which the programs are stored when they are running, and it contains the data also. The memory also uh, has the data within it, on which the operations or the programs has to be run. Now we actually divide the memory into two types, the primary memory and the secondary memory. Primary memory, which is also called as a main memory, is volatile in nature and holds the program while it is running on the system. DRAM is the most commonly used memory type in today's scenario, and it provides random access. That is why it's called as DRAM, dynamic random access memory. It provides a random access to any location. That is the advantage there. Secondary memory is the non-volatile memory, which is used to store the program and it is used to store both the program as well as the data between the runs. Between the runs, it is used to store it. Now, it is mainly as primary memory contains DRAMs. Here, secondary memory contains the magnetic disks. Magnetic disk is, which is also called as a hard disk, is a form of a non-volatile secondary memory, which is composed of rotating platters coated with magnetic recording material, which will help in storing the data. Cache memory is yet another important memory concept there. So cache memory is fast memory. It is smaller in size, but it is going to be very fast. It is acting as mainly a buffer for lower to larger memory. So whenever we need to have uh, impedance mismatch to be overcome in a system design, then we obviously go for a cache memory being placed there. So volatile and non-volatile memory, we have already discussed. DRAM is an example of volatile memory, and the secondary memory, which is the magnetic disk, is an example of the non-volatile memory. Then we move on to the removable storage technologies, which is also a part of the memory. So what are all the removable memory things that are available, technologies that are available? Optical discs, which is going to be including both the CD, compact discs, and DVDs. This constitute the most common form of the removable storage, the optical discs. Next is the magnetic tape, which provides only a slower serial access, and has been used to back up the disk in a roll, often is replaced by duplicate hard drives. That is regarding the magnetic tape. And flash-based removable memory cards, uh, typically attached by a USB connection, are often used nowadays. And floppy drives and zip drives are a version of the magnetic disk technology. The floppy disks were the original primary storage for the personal PCs, but nowadays it is largely managed, as we all know. So we have move on to the next topic of discussion in this unit, which is regarding the performance of the system. Now we till now we have seen what are all the components that are present in a system. Now we are going to see how does a computer system work with, how does it perform, how do we evaluate the performance of the components of the computer system. Now, before entering into how to evaluate the performance, we should know what are the basic components and how each is measured. So, we talk about the components of performance first. The basic components of performance and how each is measured are given here. Components of performance is the CPU execution time for a program. The CPU has an particular time that is consumed while the program is being executed. That is one main component that we have to look into while calculating the performance. Next is the instruction count. How many instructions are present to complete a particular task? That will also contribute towards the performance. Next important parameter is the clock cycles per instruction, abbreviated as shortly known as CPI. The clock cycles, how many clock cycles does an instruction constitute? Then next is the clock cycle time. So how much clock cycle time is what the user fixes is going to be the next component. Now, how do we measure units of measure? The seconds, we measure the program in the form of the execution of the program in terms of seconds. Then instruction executed for the program. What is the type of instruction that is executed for the program that is written? That will also be a very big part while we are uh, evaluating the performance. Next is the average number of clock cycles per instruction. So every instruction will keep varying. As we discussed earlier, every instruction is divided into sub-modules, and then we calculate the performance. So here we take the average number of clock cycles for a single instruction, and then we calculate the overall performance. Seconds per clock cycle. How many how many seconds do we allocate for a clock cycle is also a unit of measure. And finally, with all these in the mind, we execute or we calculate or we evaluate the CPU execution time for a program to be CPU clock cycles for a program into clock cycle time. This is the method with which we are going to calculate. Now let's move on to the CPU performance equation. So the classic CPU performance equation in terms of your count of instruction or the CPI and the clock cycle time is given as the instruction count into CPI into the clock cycles per instruction into clock cycle time. or it can also be given as instruction count into CPI by clock rate, because rate is the frequency and time is the inverse of frequency. So we can represent it like instruction count into clock cycles per instruction by clock rate or into clock cycle time. So it is represented as T, which is nothing but the CPU time, N, which is the instruction count, into S, which is the clock cycle per instruction by clock rate R. Next, now how we evaluate the performance, we have to compare it with the performance of another system. So we call it as a relative performance. So performance of A, we consider two systems here, A and B. Performance of A by performance of B is given as execution time for B by execution time of A, which is represented as N. This is how we calculate the relative performance of two systems. So initially we calculate the performance of a system, and henceforth we calculate the relative performance of a system. Next, the execution CPU time for a program. So CPU execution time for a program is nothing but the CPU clock cycles for a program into the clock cycle time. Here again, we don't take the instruction here. We take the entire program clock cycles for the entire program. And again, with respect to the frequency, that is the rate, we calculate it as CPU clock cycles for the program by clock rate, as clock rate is nothing but inverse of clock cycle time. So the CPU clock cycles required for the program is given by instruction for the program into average clock cycles per instruction. This is how we calculate the performance of a system. Moving on to the factors that will affect the CPU performance. There are many factors that will affect the performance of the CPU. That will depend on the algorithm, what type of programming language we use, the compiler type, the architecture, and also the actual hardware that is used. Now let's discuss one after the other. The first factor that will affect the CPU performance is the algorithm. The algorithm determines the number of source program instructions executed, and henceforth the number of processor instructions that is to be executed by the processor. The algorithm may also affect the CPI by favoring slower or faster instructions. It depends on how you write your algorithm. So if you use a floating point operation, for you write an algorithm for a floating point operation, then it may occupy higher CPI. So in that way, CPI algorithm is going to be one of the most important factors that will affect your CPU performance. Programming language is next, which will certainly affect the instruction count. Since the statements in the languages are translated to the processor instructions, which will determine the instruction count thereby. The language may also affect the CPI because of its features. For example, your Java will have a heavy support for data abstractions. Henceforth, it will use higher CPI instructions, whereas your C may not use much higher CPI instructions. Next is the compiler. The efficiency of the compiler affects both the instruction count and the average cycle per instruction. Why? Because why is it is the compiler determines the translation of the source language instructions into the computer instructions. The compiler's role is very complex here, and henceforth it affects the CPI. The final factor that is going to majorly affect your CPU performance is the instruction set architecture. The instruction set architecture affects all three aspects of the CPU performance. Since it affects the instructions needed for a function, the cost of the cycle of each instruction, and also the overall clock rate of the processor. So this is also very important factor that will contribute towards the performance. Next is the Amdahl's law, which talks about the performance improvement. The statement is it states that the performance improvement to be gained from using some faster mode of execution is limited by a fraction of time the faster mode can be used. Hence, we calculate the speed up as the performance for entire task using the enhancement by performance of the entire task without using enhancement. This presentation covered the basic idea about the computer organization. In the next video, I'm going to present you about the instructions and its types and the addressing modes. Thank you for now.